Welcome back. We are in the middle of our discussion of descriptive statistics. So descriptive statistics describe a batch of data. In the previous video, we talked about frequency distributions, which I think of as a very detailed summary of all the values in our distribution. And then we talked about the shape of the distribution through histograms. So as a quick review, let's just go over to the document camera for a second. We drew a picture of the age distribution, and it was slightly right skewed. So what I meant by right skewed was there is a long right tail. Now, what we're going to do in this video is discuss what I like to call single number summaries of this distribution. So this is a complete picture of what the distribution of age looks like. Now we're going to define specific numerical measures to capture specific traits of this distribution. So one of those traits is going to be where is the middle of this thing? So we call these measures of central tendency. And so another way to think about this is what's a typical age? So often statistics textbook authors use the term, typical value. Where is the center or the typical age of someone in this distribution? And so we're going to start out by going over these measures of the middle, if you will. Then we're going to talk about measures of dispersion, which is, how homogeneous or heterogeneous is this population. All right, let's get into it. So you've seen this stuff probably going back to grade school. I'm going to therefore go pretty quickly. Let's say I've got some set of measurements, and I'm going to use the notation for a population right now. So what makes this population notation is the big N. So big N is the number of people in my population usually. All right. So measures of central tendency try to characterize typical value or the middle. So the three most famous measures are the mean, median, and mode. So the population mean, if I've measured every unit in my population, is just the sum of the values divided by the number of values. Now, another measure is the median. So the way to think about the median is it divides my distribution in half. Okay, so it's the point where half the values are greater than or equal to the number, and half the values are less than or equal to that number. So as a quick example, let's say I had a list of data consisting of the values 1, 2, and 3. So where is the value that separates this into halves? Well, the value is 2, because half the values are less than or equal to it, and half the values are greater than or equal to that number, at least half the values. What do you do if you have an even number of cases? So, for example, I could have the list of numbers 1, 2, 3, 4. Technically, any number between 2 and 3 would be a median then. So 2.1, notice that half the values in this list are less than or equal to 2.1. Half the values are greater than or equal to 2.1. By convention, we usually average the middle two values. So this works whenever you have it's called an interval scale, so anything that can be measured on a number line. And so I would really say the median is 2.5. I'll just mention if you have strictly ordinal data is data where you can say one value is greater than another, but you can't say which one is, how much greater it is. So for example, if I just had we had a race and I knew first place, second place, third place, I don't know the distance between second and third place, but I know, the third place runner came in slower than the second place runner. We can compute medians of ordinal data. We cannot compute the mean of something that is strictly ordinal. It just doesn't make sense. The mode is a value occurring most frequently, and it's indicated by a peak in my histogram. Now, what you need to know about this is, number one, medians are robust to outliers. So if I have one extreme value, if I bring in one extreme value into this computation, I can make the mean as large or as small as I want. Okay, so the mean is not at all robust because I can make that value as large or small by having one extreme value. The median, on the other hand, is extremely robust in that bringing in one extreme value does not change the value of the median at all. So the classic example would be, let's say all of us have an income of $100,000, and then you bring a millionaire into the class. Well, the mean would billionaire. Let's make it a billionaire. On the average, we would all be millionaires, but the median doesn't budge at all when a billionaire is added to the class. So one more thing to note about these three numbers. I'm going to go over to the document camera for a second. Let's take a look at a right skewed distribution. I want something a little bit more right skewed than what I had before. So I'm going to give myself a really long tail here. And I just want to discuss the meaning of these statistics visually. So the median is, remember, the point where half the values are greater than, half the values are less than that. So what does that correspond to in terms of a histogram? So remember, histograms work on area. So I have to find the point, so maybe it's about here, such that the area to the left, so I'm going to do some shading to try to represent this area, has to be half, 50%, and the area to the right, so let's just go shade away over here, that area is also 50%, and this is the median. All right, what is the mean? Well, the mean is the center of gravity. So if you would picture trying to stick a wedge under this histogram so that it remains in balance. So the mean is going to be the point where this histogram is in balance. Now, you could think about these extreme values have a lot of leverage, but there's not a lot of weight out here. But an extreme value is going to pull the value of the mean out. Okay, so extreme values will pull the value of the mean out. They leave the median untouched. So if I put a value way off to the right, the median is unaffected, the mean is. Finally, the mode is the most frequently occurring value, which is the peak of this. So usually with right skewed distributions, the mode is the furthest to the left, then the median, then the mean. Likewise with a left skewed distribution, this would be our mode, this would be our median, and this would be our mean. All right, so just remember, the mean gets pulled by outliers, the median does not. All right, back to our course packet. This is something that I want to mention. I hope it's obvious to everyone, but it should just be pointed out. So ordinarily, it makes no sense to compute the mean of nominal. So nominal is a categorical variable. Like remember our fitness club example where you had book statement and two types of electronic fund transfers. You can't compute the mean payment method. I can't compute the mean marital status. But if I have a dichotomous variable, so dichotomous means two values, it only takes two values, then I can compute the mean of it. And that mean has a very special interpretation, which is it's the fraction of ones. Okay, so as an example, let's say I have 5 parts, and the value 1 indicates defective, the value 0 means not defective. All right, so the first part is not defective, not defective, not defective, then I have 2 defective parts. So if I take the sum of the values, I get 2, indicating there are 2 defective parts. Okay, so the sum of a 0, 1 variable is just the number of ones. Duh, of course, but that's something we're going to use a lot when we get to like the binomial distribution. What is the mean of this? Well, the mean is 2/5 or 40%, so 40% of the values are defective. These are really important. They're called dummy variables. You'll run into them a lot when you get to regression. Another term that you'll see is indicator variables. So just know these different terms. Now, another measure of central tendency is called the trimmed mean. Now, the way I like to think of a trimmed mean is it's something that is like a halfway house between the mean and the median. So, the problem with the mean is that it's not at all robust to outliers. The problem with the median, as we'll see in some later examples, is that it's too robust to outliers. It's just too insensitive. And so we want to find something that has some of these desirable properties of the median, that it's not affected by extreme values, but it's a little more sensitive than the median. Okay, so that's the idea of a trimmed mean, or I'm not going to teach you Winsorized means. Let's just stick with trimmed means. So what exactly do with a trim mean? So trim mean is we're going to drop a certain fraction of cases from both ends of my distribution. So I'm going to define the 10% trimmed mean as the mean where I drop 10% of the cases from either end. Now, let's go do that. All right, so the simple mean would be add up my 10 values, divide by 10. The trimmed mean would be get rid of the 20 and get rid of the 1. So I've just dropped 10% of my values. Now I only have 8 values left, divide by 8, and I get the trimmed mean. Now, earlier I called this a kind of a halfway house between the mean and the median. Let's think of another way of defining the median. So we could define the median as the 49.999999% trimmed mean. So if I were to drop, all but the middle case from the right-hand side of my distribution, and drop all but the middle case from the left-hand side of my distribution, I'm just left with the middle observation. I compute the mean of one observation, I get the observation, which is the median. All right, so therefore you could see where turning up the fraction of cases to the point where we're dropping half from both sides gives us the median. If I trim 0%, I'm left with the simple mean, and therefore this is kind of a unifying statistic in that it bridges the gap between the mean and the median. How do we do this in R? Well, in R, I'll just define my vector x. The mean function usually gives us the mean. There is an optional argument that has a default value of 0 that gives us the normal mean. If we play with this argument trim, we get the trimmed mean. I'd like to now introduce one of my favorite packages, which is the Psych library, actually developed by a Northwestern professor. The Psych library, so let's go back to R. Let's go read this data set in. And I'm going to bring in the Psych library. Has a function called describe. And so describe computes all the statistics, the single number summaries that we're talking about in this lecture, and maybe a few more. Included in there is the trimmed mean. And so, whenever I start looking at a data set, I'll just run describe on it. And all of these numbers give me a pretty complete picture of what's in the variable. Now, it's not complete. It's not totally complete in that I also want to be looking at histograms and box plots, which we'll discuss next. But I really like this this complete snapshot of my data. All right. Moving on, let's talk a little bit about measures of position. So measures of position are another way of generalizing the median. Okay, so what is the median? The median divides a distribution into two pieces. So cuts it in half. Well, a way of generalizing this is maybe we want to divide it into roughly equally sized parts. So a quantile is, divides a distribution into roughly equal sized parts. So we have various quantiles. One specific type of quantile is a quartile. So a quartile divides a distribution into four roughly equal sized groups. So let's go over, I say roughly equally to kind of cover myself when I have small discrete distributions. So if I only had 5 numbers, I can't divide it into 4 equal sized parts. If I have a continuous distribution, then I can divide it into equal sized parts. So let's just go look at this on my document camera for a second. So if I had a distribution like this, this would be my median. So the median, I'm now going to call Q2. And that puts it into 2 equal sized parts. If I further subdivide this, so let's say this is 25% of my distribution, this is 25%, 25%, and this is 25%. I'm going to call this Q1 and Q3. So I have divided my distribution into 4 equal sized parts. The quartiles are either these cut points that do the dividing. Quartile also means these individual parts. So if you scored in the top quartile of an exam, that means you scored in the top 25%. So we would call this the top quartile. We also call Q3 a quartile. So unfortunately, the term means 2 different things. Quintiles do 5 groups, deciles 10 groups, demi-deciles, so the prefix demi means half, so this is half a decile, does 20 groups. Percentile gives us 100 groups. All right, how do we compute these in R? So there is a function called quantile in R, and the quantile function, if you just type quantile on some variable, gives you quartiles by default. So it gives you quartiles plus the min and max. Now this this set of descriptive statistics is called the 5-number summary. So very important set of 5 numbers. Another place that we get that, let's go back to R for a second, is if you just do a summary on a data frame. So let's do summary on employee. This will give us the 5-number summaries of all these values plus the mean. They throw in the mean for a good measure as well. So it's very common to get the 5-number summary. What if you don't want quartiles? Maybe I want quintiles. Well, there's an optional argument to the quantile function, which is a set of probabilities. So if I said, give me a sequence of values from 0 to 1 by 0.2, well, now you'll see I have 5 equal size groups instead of 4 equal size groups, as I had before. Okay, so what we could say is that 3/4 of the people, this happens to be from my defaulting customer example, 3/4 of the people put a down payment of $175 or less down. All right, so that's the definition of quartile and quantile, how we find them in R. Now, I want to warn you, statisticians and software designers don't agree on how to define a quantile, even just a quartile for that matter. And so if you use different software, you may get different answers for the quartiles. Your answers could differ from the answers in the textbook also. So don't freak out if what R gives you doesn't match whatever textbook that you're using. They're just using different definitions. So I'm going to give you an extremely simple rule, which is I think useful for an exam. And so here's my simple rule. Go to the frequency distribution and find the first cumulative percent that's greater than or equal to the percentile that you want. So just to illustrate this, let's go back to my age example, and you're going to see that I reported the first quartile using something like describe to be 34. So let's go back to the actual frequency distribution, and we're going to follow my rule. So the 25th percentile would be the first cumulative percent that is greater than or equal to the percentile I want. So let's think about why that's the case. So let's say I stopped at 33. So the interpretation of this number right here is 22.8% of my data has a value of 33, age 33 or less. So notice I'm not a quarter of the way into my data set. So if I had these people sorted in terms of their age, the next person after the 4,288 person would have age 34. In fact, the next 492 people would all have age 34. Now, somewhere in the middle of those 492 people is the person who is exactly 25% of the way into my distribution. And by the way, the 4,780th person is over 25% of the way into the distribution, but that person still is age 34. So somewhere in the middle of those 492 34-year-olds, I've gone a quarter of the way into the distribution. Okay, so that's the way I find the 25th percentile. Let's do another problem. So what is the 90th percentile? Well, the 90th percentile is not the value 69 because I'm not quite 90% of the way into the data. The 90th percentile would be age 70. So if you don't believe me, let's go look at what the describe function does. And sure enough, it says age 70. Let's do another one. What is the 95th percentile? Well, according to this, it's 76. We go back here. I want to go 95% of the way into the data, which is here. So notice we're age 76. All right, so that's a very simple way of finding the uh, that value from my frequency distribution. So I kind of like that rule because it makes us unite two concepts, that of the frequency distribution with this new concept of a measure of position. All right, that's it for this video. There's going to be another video coming up for measures of dispersion, and you can watch that next.